Okay, I think let's get started.
Okay.
Yeah, you have the
Hello,
word.
everybody. Hello, everybody. I'm Sergio Rossi. I'm the coordinator of the construction of marine animal forest, working in the Disteva, Universidad del Salento, and also here in Brazil, in Labomar, in the Universidad Federal do Ceará. And I would just try to synthesize some ideas that are just what we can put on the table to be sure that we are all understanding some of the points, because for management, and especially for many future plans that we already have of conservation and restoration, some things have to be important when we talk about the carbon that is just flowing on the one side, but also just be fixed during the structures and in some in other forests, also in the sediments is accumulated. Okay. So it is important to understand this, and just starting with this ecosystem engineer approach, in which all these organisms are facilitating the life of others, you know very well. And above the water, it has been very well described by John in 1994, because this ecosystem engineer topic, ecosystem engineer description, and it's easy to understand in the on land how an ecosystem engineer works. And also, if you want, on the water. On the water, we know that there are many animal forests, many forests, many different kind of forests that in some way work as they work on land. Of course, there are differences. Of course, there are different concepts that maybe you have to be well described, but in the end, the three-dimensional life structures have the opportunity to shelter organisms, to provide food, to provide ways to make these organisms, provide niches of survivorship for many species. And the productivity of the marine forest is huge, especially, for example, in the vegetable ones. We have here seagrasses and seaweeds, in which you have this continuous flowing of carbon in this area due to the fact that they have seasonal cycles. There are many things that have to be still described in the marine animal forest, which are composed basically by suspension feeding organisms, sponges, bryozoans, gorgonians, ascidians, and so on and so on. And I want to just focus your attention on the different kind of marine forests, like for example this, which is calcium carbonate based marine animal forest, the coral reef at the shallow waters in Polynesia, or this one, which is practically not a forest, probably a shrub, okay, but also three-dimensional structure that is also concentrating calcium carbonate. But other forests, like for example the Gorgonian forest in the Caribbean Sea, not only have this calcium carbonate accumulating, but also in the case of Gorgonians, carbon that is fixed and is stopped during long periods of time, as we will see, in these three-dimensional structures. Some of the forests, like for example the mesophotic forest, or even the deep forest in Greenland, have still to be described as forest, because the concept of forest is a little bit vague. Let me explain. We still have to understand what we understand by a forest, or what we understand by, for example, a savanna, in which you have few trees that are there living, and they are there also intercepting the wind in the case of a savanna in Africa, but are not true forests because they can be sparked. Like for example, these gorgonians that probably, more than probably, are changing the hydrodynamical fluxes, but not to the extent to indeed change the near bottom system properties and the kind of, this kind of interception of particles, of nutrients, and so on and so on. But even though we do have true forests all over the world, and also I want to just that you pay attention that again, not all these forests are based on calcium carbonate. Of course, you know it very well. And we have been paying attention to the coral reefs, which are based on these Caribbean organisms that may build up islands, that may build up huge structures, the middle of the Pacific or in the Indic Oceans. But also the forests have carbon that is fixed again in these structures, the alive three-dimensional structure, during decades or during centuries or even millennia. So we normally understand this kind of approach on the forest that are based on calcium carbonate, like for example, Corallium rubrum, it is an octocoral that has the capability to stop carbon, to just immobilize carbon during a huge period. But we are not probably considering sometimes the other kind of forest that also may be more labile in the sense of having a shorter capability to maintain the carbon retain, but they may be also important. The cold-water corals is also another example of calcium carbonate that is stocked, but is mixed with other organisms, like, for example, sponges and gorgonians sometimes, that are not fully calcified or are not calcified at all. Remember that, for example, in other places, the base of the structure is silica, like, for example, in Antarctic sponges. Many of the Antarctic sponges are desmos sponges or silica sponges. So we have to make and understand much more in depth what we understand by the fixation of certain elements. And we are addressing the point, we are focusing the point to the carbon. So let's talk about the carbon. This, I love it, this drawing from Barnes, Deca Barnes, David Barnes, have been published in 2018, in which he studied let us say, the carbon stock in Antarctica, okay? And if you see here, okay, there is an algal bloom, okay, about several, hundreds of tons per kilometer square per year, okay, that are just fixed. The CO2 is fixed from the flux that comes from the atmosphere and is entering in the loop of the microphytoplankton. This is eaten by benthos, both directly or indirectly. Maybe it's eaten directly the phytoplankton by filter feeders, or maybe it's eaten the zooplankton or the detritus or the bacteria that are produced, but that all are coming, basically all are coming from this primary productivity. From this eaten by benthos, there is a benthic growth. So the organism grows in part due to the flux that is coming from the heterotrophic flux that is coming from this carbon. And this benthic growth, okay, remains partly immobilized as carbon in structures. Okay, the carbon sink can be considered, is considered the carbon that is fixed for really long times. But we have also to consider a little bit this immobilized carbon, because many of these structures may last, some of them for 1 year, as we will see, but some of them for centuries, millennia, tens of thousands of years, or even more, as I want to highlight. This is the pathway of heterotrophic organisms. So all the suspension feeders, as you know, are heterotrophic, but some of them are also autotrophic. So also they can just rely on the small symbiotic that are just translocating, making translocation of energy in terms here, okay, of photosynthesis. So in terms of amino acids, in terms of carbohydrate, in terms of short chain fatty acids that are going to the mitochondria and to the organism, to the animal organism. And this makes possible not only respiration, but also the growth of the tissue, the alive tissue, but also helps, energetically speaking, to the calcification of this structure. So here is the first question. First question, to me is there is an immobilization of carbon. There is, there has been a lot of discussion, especially in the late 90s, early 2000s, about the source or sink of the coral reefs, for example. But what I want to just stress to you is that even if, of course, the geochemists stress this point, even if there is not a net gain of the calcium carbonate, in the sense that when you are doing all this operation, not all the carbon entry is just automatically fixed. Okay, we have this stoichiometric balance that relies in the balance between the different components. But what is true is that part is immobilized in form of calcium carbonate. So that starts to be interesting because, of course, it's not a carbon sink. It's in the sense, or maybe not considered a carbon sink. Again, there are a lot of discussion about that, about the world system. This is why I love the last presentation about this kind of the complex system in which you don't have only one organism. Like, for example, the coral, you also have the macroalgae, you also have the ascidians, you also have other organisms that all of them perform synchronized, if you want, biogeochemical cycles. But it's important to understand that both in this case and in this case, we are immobilized carbon. So we have the opportunity to look at the immobilization of carbon in these structures. And this is one of the things that I want to discuss. And I want to just put on the table, not only here, but also in the future communication that we want to do after the workshop. So now, what is interesting is that we can calculate. This is, for example, a Gorgonian, a Gorgonian population here in a rocky substrate, and we can calculate the biomass of these Gorgonians, and we can calculate also the quantity of stock carbon in the Gorgonians from pictures or from remote operated vehicle approaches. So we can make, and it's not, there are very few works made on this way, to just understand how much of this carbon is stocked and during how much time, sorry. So we can do that. We can just understand the static vision of this population, for example, of Gorgonians, through a specific software and a specific approach with the images. And we also can calculate, for example, in this case, the quantity of carbon that is just stopped in some way, is immobilized during a certain period. Okay, looking at the same species, the same coral, and make the calculations of the carbon again, and also other elements that are just, again, immobilized in these structures and during how much time. It is important to understand that then we can process information, selecting species, and looking at the world picture, and trying to look at the world ecosystem. It's impossible, of course, to calculate all the growth of all the species, but we can select some species in which we have, or from literature, or from experiments that we want to do, experiments that we want to make the follow-up about the quantity of carbon that can be just in some way stocked in these structures. And that for me is quite interesting. One of the things that then we have to understand is that what we are seeing in many places probably is not exactly what has been the reality in terms of the mature forest all over the world. And this is because in some way, it has been suggested that many of these organisms, especially the clonal ones, so especially the Heteroparous, so the organisms that are long-lived, like, for example, some of the corals, scleractinians, sponges, in some way, which are not clonal, but are just the massive organisms in which you have a tendency to occupy as much space as they can, and are just following a little bit the thinning rule. This thinning rule makes you to understand that it's not exactly the same having a small forest in which you can accumulate a certain quantity of carbon than, a central. Let me just explain this easily if you want, or even not very properly. The winner of the space in the area in which is concentrating a lot of energy and a lot of capability, a lot of possibilities, sorry, to reproduce. The larger the organism, the larger the possibility to create, in this case, seeds, because it will have more flowers. In the case of the coral, for example, or in the case of a gorgonian, or in the case of a big bryozoan, the more is large the organism, the more capability to analyze the fluxes of the ceston or the light, okay, and the symbiosis, and then having more foliage or having more zoanths or having more, parts that are just making possible the growth of the gonads, but more possibility to maintain their populations and to spread, the new recruits, not only nearby, but also to more, far distances. So for me, it's important, this concept, because this is what we have. This is red coral, Corallium rubrum, 1975 in Costa Brava, okay, 35 meters depth. This is the coral, the red coral that we have just a few decades ago. And this is a very well performed, quite very well performed red coral. We don't know the age. We don't know, maybe 150, 200 years. Indeed, still, we have to understand how many years it will stand. But what is true is that this is at the same depth, the red coral that you find in some places in the same area. So we passed from a tree forest to a grassland. And this stocks a lot of carbon, and this stocks less carbon. How? How much carbon this stocks, and what is the flux of this carbon? This is the question that we have to put on the table. Of course, if we want to understand in this very slow growing species, we have to make an experiment of something like 200 years to understand exactly what is the rule of this kind of forest in the carbon cycle. So it will be a little bit difficult. And the concentration of the carbon that is just coming from the ceston, this is an heterotrophic species, the red coral, Corallium rubrum, which is fully heterotrophic. The quantity of carbon that is in some way flowing from the water column, the foliage, and from the foliage to the next, to all the overall structure, and also the calcium carbonate that is fixed, that is just stopped here to produce all these primary, secondary branches, so on and so on, will be very different from this one. But this is a question that for this long-lived species, it's very difficult to calculate. This is why, just briefly, I will just try to show you an experiment made many years ago, okay, based on the anhydrozoan and Evrelium racemosum. Evrelium racemosum is an hydrozoan, is a carnivorous hydrozoan. It's an opportunistic organism. It's everything that is in the water column. But you can find these heterotrophic species. You can find copepods, naupli. You can find the larvae of different invertebrates. You can find also detritus. You can find many preys, and it's concentrated. What is very interesting is it has an annual cycle, and during this annual cycle, let me just put in this way. It's coming from this, let us grassland to this kind of huge tree. And why is interesting this species? Here, what you have is that you have here the temperature, okay? This is the temperature in the Mediterranean Sea, okay, during an annual cycle. Look at it is 3 to 5 meters depth. Look at the maximum temperature of 24 degrees. Unfortunately, this is not the case now. We arrived this year to 30 degrees centigrade, the first 5 meters some places. So things are changing very, very fast. And this, has a follow-up of the height of the colonies. So the tallest colonies from here, more or less, June, more or less, May, June. And in May, June, in fact, the thallus colonies have more polyps, and having more polyps have the capability to reproduce. In fact, the reproduction of these organisms is here, concentrating as much as they can carbon in single trees that are less dense. The density is decreasing from February to May, June, and then is again, decreasing again. And not only the height, but also the density is decreasing. The height is decreasing, the density is increasing again when the organism has the opportunity to just. But the most important thing here is this. The most important thing is that during a certain period, if you see, this is the height of the colony, 0.5, 2 centimeters height, 2.1, 4 centimeters height, more than 8 centimeters height. Okay. You find here in this graph, looking carefully, that this 0.5, okay, to 2 is disappearing, okay, here it's completely disappearing, and you find some of the colonies that are more than 8.1. Most importantly here is the flux, the milligrams of carbon that are coming from the prey, okay, that are per unit of carbon per meter square per day. Okay, so this is the flux of carbon here, okay, related to the carbon of the structure. So here you have in some way a tree or trees that are tallest trees, and here you have much more present all these very small trees that are not concentrating so much energy in their structures. So here you have that during the whole year, the organisms are tending to be less dense and much more higher and ramified. So they have more ramifications, and these ramifications have more polyps. They can capture more energy, and this energy is just, translocated for what they need, reproduction. As all the organisms in this planet, alive organisms in this planet, they need to reproduce, and then they need to focus on to concentrate the flux to the reproduction as much as they can. If we see here, there is a tendency, okay, and a negative exponential curve that is just broken here by a couple of months in which this is not working. So the colony density here, okay, is low, but the mean colony weight is low. And what happens here? This coincides basically with July and August, in which these little guys are coming and are eating in some way. They are preying upon the hydrozoans, not only the polyps, but also the fertile polyps. So the gonozoids that are present in the hydrozoan, and they are just feeding on that. So this accumulation of carbon here in these trees, okay, is, this organism, this nudibranch, it's Flavellina finis, is taking advantage of this huge concentration of carbon additives here. For me, the take-home message here is basically that these benthic suspension feeding organisms, many of them, not all of them, but many of them have the tendency, if they are long-lived, to make this kind of three-dimensional structure as bigger as they can, concentrating carbon. And also we may just have this example with short-lived organisms like this hydrozoan, which once a year concentrates as much as they can the energy here and reproduce to just use all the accumulated carbon for the next generations. So my question here is as follows: how much time this carbon is stopped? How much time indeed this carbon is immobilized? For me, it's important because this is the thing that we have to understand to make basically this kind of, or try to, I think that Nikos in the next talk, we will talk about a little bit about this use or something new use of the concept of blue carbon and the capability of these organisms to stock the carbon and being used as an ecosystem service, which is good because it's an ecosystem service. In this case, in some ways, taking the carbon and immobilizing. But how much time? In the case of the hydrozoan, it's clear that the return to the system is basically during 1 year. Nonetheless, of course, it change, and you might have to make proper calculations. But you have this, let us say, grassland hydrozoan performance up to this kind of three-dimensional alive structure that is just making these big trees, more than 8 centimeters height, with all this carbon accumulated. In the case of other organisms, like, for example, gorgonians, they last decades to grow, and this growth is, again, stocking carbon. So how much carbon is stocked and how much time is stocked? So that's, for me, the important thing. When we focus on this question, we may understand that this kind of three-dimensional structures are indeed alive in the sense that they are just taking all this carbon, immobilizing the carbon in these structures, and making possible that part of this carbon is not released again to the system. Not only in terms of calcium carbonate, but also in terms of gorgonin, for example, or other structures, proteins or molecules that are that are just taken from the cestone, or in the case of mixotrophic organisms, taken from the cestone, of course, because all of them are heterotrophic, but also because of the autotrophical part, which distributes from the photosynthetic map. So this is the question: it's how much time and how much of carbon is stored. Here we have two examples of extrapolation that we have made, very simplified, but that starts to work. This is very simple. This is tiles, okay, d-dimensional tiles, put on during 3 years approximately, put in a 20 meters depth area, and then after the 3 years, observe and calculated the carbon that had been stocked in the seaphilic part, in the part that is just sheltered from the light and also from the excess of sediment and so on and so on. Basically, what you find here is most of them are polychaetes, okay, which are just accumulating calcium carbonate to shelter the organism, the delicate organism that is inside the worm. And also there are many other organisms here. So here you have, on the one side, organic carbon that comes from not only the fleshy part of the polychaetes, but also from acidians or for bryozoans, not calcifying bryozoans, and so on and so on. But then you have also a carbon that is stocked during a while for these 3 years. Of course, there are, many processes here during the 3 years, and you see a static picture. But in the static picture, in which you are looking for the inorganic carbon, so the calcium carbonate, we saw that if we have an extension of 10,000 meters squared, so 1 hectare, okay, we may have to 1.9 tons of carbon per hectare and per year. If you look in this, take into account the 3 years, dividing, of course, and simplifying the thing for 3 years, is what the people is doing also on the forest. And the forest, when we talk about carbon, people is looking at the stock carbon and the sunk carbon, and look at the carbon that is immobilizing this during a certain period of time. And we find that simple organisms like this stock quite a lot of carbon. It's much more higher than we previously thought if you compare with other areas, with other terrestrial and also aquatic areas. The same kind of approach has been made, but in this case, with integrated multi-trophic aquaculture facilities, in which what we did is just put these ropes with floaters, okay, which we cultivate passively, in the sense that we just put the rope in the right moment to, let us say, leave the organism, the larvae, to settle down in the rope. And we have all these organisms, that the macrofaulers, that were just attaching to the rock. So the rock has a lot of, this a certain quantity of different polychaetes, sponges, especially also bivalves, and so on and so on. And what we saw is that in this, if you calculated for 1 hectare, we may have 5 tons of carbon per hectare per year with this methodology. Of course, you will say, and you will say right, that in this case, for example, most of the carbon is organic carbon. Some of this organic carbon is labile and will just return to the system. However, it's not so easy to just decompose. It's not so easy to, for example, the tubes of the polychaetes is not so. But in any case, it may return to the system. But this is the point. The point is that what we are doing here is during 1 year, the huge, well, a little bit of more than 1 year, 16 months, this huge biomass is growing there. And then we have to think about it, how to manage this biomass if we want to indeed make this kind of carbon uptake and make something with that. This is because it has been just, saying that, no, the kelp, for example, kelp and macroalgae are carbon sinks and are blue carbon and so on. And I would say, well, depends. If you take into account the natural cycle, I'm working now in Punta Arenas with Professor Americo Montiel, and we are looking at the numbers. And if you take into account the natural cycle, so what happens during the natural cycle, which you see that this part is decomposed and returns to the system. So you are not stocked with the carbon during a long period. This carbon is stocked for a while. This carbon is stocked just for 1 year, 1.5 years, and then it's decomposed, and it's part of the diet of many other organisms, and then I can go to other organisms that are just grazing or deposit feeders that are taking advantage of the detritus. So this is the question: is which is the elapsed time? But you have to think that many people is just looking at this carbon also as an opportunity, because if you harvest this carbon as the carbon that is stocked in the integrated multi-trophic aquaculture facilities, if you take and you harvest this carbon and you take this carbon and utilize this carbon in another way to mobilize the carbon, maybe is a way to just help, for the mitigation. Of course, it's a question of scale, and this is one of the most fragile things. If we do that in 1 hectare, we do nothing. If we do that in a couple of hectares, we do nothing. Normally, this kind of approaches take into account few, meters squares or 1 hectare, something like that. And then you are not mitigating nothing because you don't have the possibility to stock much carbon. That's the reality. But if you think, and if you take into account larger areas in which you, for example, make restoration plants with long-lived organisms, or you take into account this kind of approach of integrated multi-trophic aquaculture, or this kind of stocking carbon with macroalgae, the people that is working with macroalgae many times say, yes, the problem is the scale, but we should, or we can, or we can propose to make larger areas in which we uptake this carbon, and then possibly there will be a mitigation, a small mitigation. I would say a small mitigation, because with the quantity of tons that we are moving with CO2, it's difficult to talk about this kind of mitigation effect if you don't do that in square kilometers, hundreds of square kilometers, which is really complicated and not straightforward. So many of these marine animal forests are spread all over the world. And look here, for example, which is a coral reef, how much carbon may be stocked here for long periods. And even more, if you think about the organisms that are just living in the sea mountains. Okay, so we do have to understand that the carbon there is largely stocked. Some of this carbon has been largely stocked for hundreds of years, or even more. And we have to understand that if we lose the possibility to not only conserve, but also to make a repristination, a rewildering of the benthos in many places of the world would be difficult to, first, as has been said, to make possible the, the functionality, make possible again that the system functions again because of biodiversity. Remember that all these marine forests are biodiversity hotspots. But also, if we have the opportunity to just make this kind of carbon immobilization much more broader, we make this kind of rewilding in some way through conservation or through restoration, that will be, from my point of view, great for both things, for the functionality of the system, again, for the biodiversity, and also for the stop of the carbon and the associated biomass of fishes, of mollusks, of crustaceans, and so on. Finally, this is the last slide. Indeed, I love this slide because it's very sad on the one side, but on the other side, make you understand that things change dramatically. But nature just goes on and at the end makes possible to represent this kind of complex and long-lived structures. Here you have in the 18th century, okay, this is a drawing in Sicily. And if you look carefully, these guys are harvesting coral. They are almost naked. They have no fins. And they are taking corals probably at 5, 7, 10 meters depth. And look at the size of the coral. Of course, it can be a little bit exaggerated. It's a drawing. But if you see from the museum that is in Torre del Greco, you understand that these branches existed. And the carbon stock here probably was also huge. So if we have the opportunity to just go on with this kind of approaches of conserving, rewilding the benthos, it is possible that in another way, not exactly in the same way, it's completely impossible to represent this kind of forest anymore. But we can just have a consistent ally that allows the functionality of the system and also the capability to stop part of the carbon that will depend, of course, on what we are doing in the near future in terms of management.